So let's begin with a review of fields. So suppose that we're given a set F, and that set F has two operations on it of plus and times. Now we'll further assume that certain properties are satisfied. The first property is that the operation plus is going to be an associative operation. So it's a binary operation. Second, we assume that there is an additive identity for the operation of plus, and quite naturally we'll call that 0. Thirdly, we'll assume that for every element in the field that there exists an additive inverse, and that additive inverse is an element of the field. And finally, the operation plus is going to be a commutative operation. Now, if we have all four of those things and we put those all together, what that really means is that F with the operation of addition actually forms what is called an abelian group. Now that we've got an abelian group, let's see what extra additional structure this operation of times can add on. Well, again, we'll begin by assuming that the operation of times is going to be an associative binary operation. Second of all, we'll assume that we do have a multiplicative identity, so that we have an element 1 that's going to be an element of our field. Thirdly, we're going to assume that the distributive property holds. And finally, we'll assume that the operation of times is going to be commutative. Now, if we put those four properties together with the fact that we're an abelian group, what this does is to turn F into a commutative ring with identity. If we go one step further and assume that every non-zero element of F is also going to have a multiplicative inverse, then what this does is to turn F into a field. Now, the structure of being a field gives us certain properties, so let's actually take a look at some of those properties. Now, these are a little bit of a review, and so probably if you want to go back, we'll use them without proof, but I would refer you back to a class on abstract algebra in which these things are proven. So we'll go ahead and use them without proof. We'll just go ahead and go through and state them. So our first field property is that if we have two elements A and B of our field, then the equation x plus A is equal to B is going to have one and only one solution. For our second field property, if we've got two elements A and B of our field, and A is not going to be equal to 0, then the multiplication equation A times x is equal to B. It also has one and only one solution. Now, for our third field property, if we take any element of our field, A, and we multiply it by 0, well, 0 times A is just going to be 0. And for the fourth property, if we pick any element of our field, we know we've always got additive inverse, and so what this property is actually telling us is that the additive inverse of the additive inverse of A is the original element A again. Again, we'll kind of use these without necessarily proof, but those proofs are provided in probably somewhere that you've seen them in abstract algebra. Now let's take a look at our last four field properties. So our field property F5 is really just telling us that if we have any non-zero element of our field, that the multiplicative inverse of the multiplicative inverse of A is actually A again. For our field property F6, if we have two elements A and B that are in F, then this is saying that the additive inverse of the sum is actually going to be the sum of the additive inverses of A and B. For our field property F7, if we have two elements A and B in our field with A not equal to 0 and B not equal to 0, then the multiplicative inverse of the product of A and B is actually the product of the multiplicative inverses of A and B. And finally, for our last field property, if we have an element A in our field, then one way of obtaining the additive inverse of A is really just by multiplying A by -1. And so finally, this gives us all of our field properties. Again, hopefully you've seen these along with their proofs in some kind of abstract algebra setting. Now, we already know lots of fields. Fields that we probably are familiar with, the rational numbers. We're familiar with the real numbers, the complex field, and maybe even finite fields, where one type of finite field, if we take a prime number, then if we look at just the integers mod p, then that's going to be a field. More generally, if n is a positive integer and again p is a prime number, then if we take q to be the p to the nth power, then we can take an irreducible polynomial of degree n over the field of p elements. And then if we do the quotient group of fp, so if we do the polynomial ring over the field of p elements mod our irreducible polynomial, then we get a finite field of order p to the n elements. Now, what we really want is a further structure so that we can narrow the field. Get it? We're talking about fields, so we need to narrow the field, pun intended, down to only the real numbers. So we've got this, all the field axioms that we've talked about so far apply to each one of these fields, and so we need additional structure to kind of single out the real numbers as being the real number. So what is it that actually makes them important? Where do they actually fit in the grand scheme of things? And so that's going to be our goal from here on.